I think we're going to go ahead and start, and people can slowly trickle in.
Okay, sounds good.
So, welcome everyone. Bonjour, bienvenue à la conférence scientifique d'aujourd'hui. I see a nice cookie in front of Dr. Santosa. It's a pleasure to welcome Dr. Santosa. She's a professor at Concordia University in the School of Health, Kinesiology, and Nutrition. Her specialty is the study of the relationship between nutrition, obesity, and metabolic health. A very, very trendy topic. Goes well with the cookie.
Yes.
That I'm trying not to get the big jars in the kitchen, and I'm really trying not to go for it.
I think Christine thought I needed it for my nerves. I was freaking out looking for parking.
No, she's conducting the study. She brought a big tub.
Oh.
She's seeing how long people is. Dr. Santosa is a holder of a Canada Research Chair in Clinical Nutrition. She's received grants from NSERC, HSF, CFDR, and CIHR, trying to understand the relationship between obesity, fat, and metabolic health. Dr. Santosa, Mike is yours.
Thank you so much for your kind introduction. It's so nice to be here in person with you today. I think I was telling Shantae over email that when I do presentations over Zoom, I always feel like I'm talking to myself, and it's just very awkward. So I'm so glad we're back to in-person presentations. So first I was asked to put up a conflict of interest slide. There are no conflicts of interest to declare. And in terms of the objectives of this talk, I want to be able to discuss how obesity echoes aging and explore the underlying mechanisms that contribute to these similarities, because I understand that there's an interest in aging and this in aging research. So the learning objectives we have today are to identify at least 3 comorbidities of obesity that occur with aging, describe 2 characteristics that shift in adipose tissue which promote aging, and to list at least 3 biological or cellular mechanisms shared by obesity and aging. So fundamentally, we know that excess adiposity results in obesity. But how do we know when someone has obesity? Well, as you know, there's lots of ways to diagnose obesity. A main one, but not necessarily the best one, being body mass index. And it's well established that those with a BMI over 30 are considered to have obesity. However, as many of you know, BMI has many limitations, in fact, including the fact that we can't tell what a body composition a person has based on BMI. And the reason I felt compelled to present this fundamental information, which I know many of you probably know, is because last Thursday, a Lancet commission came out that will hopefully change the way obesity is diagnosed. In their commission, they recommend that obesity be diagnosed by either this or this or this. So at least 1 measurement of body size and BMI, or at least 2 measurements of body size, regardless of BMI, or a measurement of direct body fat, such as a DEXA scan. So what do they mean by the measure of body size? Well, measures of body size would include waist circumference, a waist to hip ratio, or waist to height ratio. So any of these can be combined with BMI, or any 2 measurements can be combined to help with the diagnosis of obesity. Pragmatically, they also have the caveat that if someone has a BMI over 40, we can assume that there is excess body fat present. So the commission went on to then define preclinical compared to clinical obesity, and there's a bit of a continuum from preclinical to clinical. And the preclinical obesity is considered a bit more of a healthier state, whereas the clinical obesity is where we have alterations in organ function, and that's when we have the more diseased state with obesity. So, typically there's been a debate as to whether obesity is a disease. So here they kind of clarified it in that in some cases, obesity is more like a disease state, but you can have healthy obesity, in other words. So in most of the studies I'm going to present to you today, a lot of the participants that we included are those with preclinical obesity, with the exception, I think, of 1. So as we move from preclinical to clinical obesity, we know that there's a number of comorbidities that can manifest, and that includes things like cancer, cardiovascular disease, respiratory diseases, your gastrointestinal, musculoskeletal, of course, type 2 diabetes. 90% of those with type 2 diabetes have obesity. There's your neurological and psychosocial, as well as various other disorders, including kidney disease, complications during pregnancy, whatever. But if you look closely at these comorbidities, you can see many of those comorbidities actually reflect aging. So if you can, in fact, you can probably substitute aging in the middle of this, and not much will change with regards to the comorbidities, right? So already we're seeing some parallels between obesity and aging. So I really consider obesity kind of as a disease that echoes aging in many ways, and we're going to be talking about that. And ultimately, obesity decreases life expectancy. Here, I'm showing you a figure where we have the males on the top and females on the bottom. What I really wanted to point out in this graph, so this is years of life lost on the left, and then we have body mass index increasing going that way, okay? So as you can see here from this figure, there is an increase with regards to the years of life lost as we progress down towards increasing BMIs, all right? And moreover, as you can see from the height, so the lighter the color, the younger the age versus the darker colors, which is like the older age, okay? So what you can see is after the age, after BMI of 30, we start to see an increase in the years of life lost, especially in younger individuals, right? So this indicates that younger individuals with obesity have that shorter life expectancy, further supporting the idea that obesity accelerates aging. We published a review a few years back where we dug deeper into the underlying mechanisms by which obesity and aging may contribute to morbidity and mortality. And we found that obesity mirrors aging at multiple levels, from the more molecular and cellular, and that contributes to factors that are secreted that also indirectly and directly affect the development of various diseases. And many of these over here are some that some that I will discuss today. So in our lab, one way in which we examine how obesity might affect our physiological age is through studying those who've had obesity since childhood. This is because children living with obesity may develop many of the comorbidities that are normally seen in adulthood and exhibit characteristics of aging. For example, we have type 2 diabetes, like children with obesity have greater risk of type 2 diabetes, greater risk of lipidemia, greater risk of hypertension. These were previously only thought to be diseases or conditions that we see in adults, right? So therefore, the main question we aim to answer is how whether those with childhood onset obesity may be different than those with adult onset obesity from the biological and physiological perspective. So as you may know, obesity to have the chronic low-grade inflammation that we see in obesity is often thought to contribute to the increased risk of metabolic comorbidities. We examined whether age of obesity onset affected some inflammatory markers, and we saw that neither in childhood or adult onset obesity were there differences in the inflammatory markers. In fact, the only difference we saw here was leptin. And that difference in leptin is actually a function of percent body fat. So there's not really in the end much difference between these inflammatory factors that we found. So then what is it that might contribute to an increase in disease risk in those with childhood onset obesity? Well, as I previously showed you, excess adiposity results in obesity. And as I discussed, obesity increases the risk of various comorbidities. So if excess adiposity results in obesity, and obesity results in the risk of these increased risk of these various comorbidities, then it must be there must be an important role of excess adipose tissue in that comorbidity risk. which is why we therefore focused on examining the characteristics of the adipose tissue that might be contributing towards disease risk. However, as you know, not all obesity is the same. Individuals with the same weight can have vastly different body fat distributions and different body shapes. In some, they may preferentially store fat in the lower body, and in others, they may preferentially store fat in the upper body. And where fat is stored is significant, because with regards to the risk of obesity-related comorbidities, we know that visceral adipose tissue increases the risk more than subcutaneous adipose tissue, right? So a lot of studies that compare both the subcutaneous adipose tissue and visceral adipose tissue have shown that visceral adipose tissue is more pathogenic. But if you think about it, at any given weight, 80% of our fat is from subcutaneous adipose tissue, right? Like most of our fat in our bodies, by far the majority, is subcutaneous adipose tissue. In lean males, visceral adipose tissue only makes up 10% of the fat that we've got. And in lean females, visceral adipose tissue only makes up 5% of the fat that we have. So considering the relative quantities of subcutaneous and visceral adipose tissue, though per gram visceral adipose tissue might be more pathogenic, the relative amount of subcutaneous adipose tissue makes it an arguably important player in obesity-related pathogenesis. So subcutaneous adipose tissues, especially in the lower body, are thought to be safer places to store fat. Our view is that as subcutaneous adipose tissue increases and expands, it starts to develop a sort of dysfunction where we have impaired characteristics of subcutaneous adipose tissue. And that dysfunction in subcutaneous adipose tissue can directly affect an increase in metabolic disease risk, but also indirectly increase the risk of metabolic disease through increasing visceral adipose tissue. In other words, if our subcutaneous adipose tissue cannot expand properly, cannot function properly, well, the fat has to go someplace and then it goes in and around the organs. Okay. So on closer look of the adipose tissue, we see that there's not only adipocytes and blood vessels. There's other things that include immune cells. We've got some dead adipocytes. We've got some adipocyte precursors and a bunch of other things. And as adipose tissue expands, this microenvironment starts to become sick. And this is a shift occurs because there's a shift in this microenvironment that then affects adipose tissue function. So the first study I want to show you is a study that we conducted to examine the immune cell profiles in those with childhood compared to adult onset obesity. We recruited females with the childhood and adult. So they in childhood onset obesity, those are females who've had obesity since pre or peripuberty. And those with adult onset obesity developed obesity over the age of 18. So their average age in these individuals was 30 years of age, and BMI was 34 in these individuals. But importantly, as you can see here, our groups were very similar with regards to body composition as measured by DEXA and CT, actually. So first, if we look at the M1-like macrophages, those are our pro-inflammatory macrophages. Here we have childhood onset obesity in purple. And as you can see, in the abdominal depot over here, the amount of M1-like macrophages is actually lower in those with childhood onset obesity compared to those with adult onset obesity. In the femoral depot, they're very similar. And then if we look at childhood onset obesity, there's no differences between abdominal and femoral macrophage, M1-like macrophages. Whereas in the adult onset, the abdominal adipose tissue had greater M1-like macrophages compared to in the femoral subcutaneous adipose tissue. We also looked at M2-like macrophages. Those are thought to be the anti-inflammatory type macrophages, and we see no differences between our groups and between our depots. And then we, with regards to the T cells, the CD8 T cells, we can see that femoral adipose tissue was had greater CD8 T cells than the abdominal subcutaneous adipose tissue, but there were no differences between groups. And this is similar with our T helper cells. Okay, so the next study, next we wanted to see a study where we compared those with like the aging compared to the age of obesity onset. So here we had 80 female bariatric surgery candidates. And this is so weird because this is the wrong slide. Sorry, I cleaned it up and it looks, I don't know why it's like this. But anyway, we had individuals, we had 4 different groups. We divided them. I'm sorry, I know that 55 is not old. I do not consider 55 old, but that's what we had in our cohort. Like that's what we could match. So these were younger adults under 40 and older adults, let's say over 55. Unfortunately, we named our groups young and old. So sorry for that. But in any case, we have the 80 female patients categorized into childhood onset younger adults, adult onset younger adults, and then childhood onset older adults and adult onset older adults. So there we go. Okay, sorry, because I don't know what's going on with this slide. But in any case, we matched these individuals, like individual to individual, according to BMI, diabetes prevalence, age, and age of onset. So this was kind of like one of those freezer studies where we had like a huge cohort of people and we were able to kind of pick out who we want, what tissue we wanted to measure. And here, age of obesity onset was self-reported. We measured various metabolic parameters, or there were measured various metabolic parameters that we were able to examine. And then, oh, see, this was the right slide. So I don't know what happened. Okay, let's just skip that. Okay, so in examining our groups, we looked at macrophages. And as you can see here, those with adult onset obesity, regardless of whether they were young or old, had significant differences between their adipose tissue depots, where abdominal subcutaneous adipose tissue had less macrophages than the visceral adipose tissue depot. Okay, this indicates that age. Here's also a trend, as you can see over there, but it indicates age and possibly maybe age of obesity onset may have an effect on adipose tissue macrophage populations. Then with regards to the pro-inflammatory M1-like macrophages, we saw that in adults who were older, regardless of whether they had childhood onset or adult onset obesity, there were greater M1-like macrophages in the visceral adipose tissue compared to in the subcutaneous adipose tissue depots, indicating that age and not onset potentially may have an effect. And in M2-like macrophages, in the childhood onset group, there were significant differences between our depots, where visceral adipose tissue depot had a greater amount of the M2-like macrophages compared to the subcutaneous adipose tissue depots. That's the abdominal. So indicating, again, age of obesity onset could have had an effect, maybe. And the other thing we looked at is adipose tissue fibrosis. And as you can see here, there were significant depot differences in our adult young, adult old, and child young groups, where there was actually more fibrosis in subcutaneous adipose tissue compared to in visceral adipose tissue. But contrary to what we might have thought, in the child old group, there were no differences between the depots. And in fact, they had significantly lower amounts of fibrosis in both the abdominal subcutaneous and the visceral adipose tissue depots. But so we weren't actually sure what to make of this, because the role of fibrosis on metabolic disease risk is somewhat unclear. It's usually thought that increasing fibrosis may increase metabolic risk. Fibrosis has been shown to correlate with insulin resistance. And others have also hypothesized that fibrosis may be beneficial through limiting adipocyte hypertrophy and improving systemic metabolism. So in other words, we don't really know. The role of fibrosis in disease risk seems that we still need to determine. Since those with childhood onset obesity are at much greater risk of type 2 diabetes compared to adult onset obesity, in fact, they're at about two times greater risk, we also examined acetyl-CoA metabolism. And metabolism of acetyl-CoA is associated with diabetes risk. So, for example, those with diabetes, there appears to be a downregulation of genes associated with the acetyl-CoA network in adipocytes, implying metabolic dysregulation. Acetyl-CoA is generated, as you know, from various macronutrients and the catabolism of these macronutrients in the mitochondria. And in the fed state, acetyl-CoA condenses with oxaloacetate to form citrate. Citrate can then leave the mitochondria into the cell cytosol, where the enzyme ATP citrate lyase, which is ACLY here, can convert citrate back into acetyl-CoA, and then it can then proceed to towards de novo lipogenesis or other acetylation reactions. So interestingly, in mice, adipocyte ACLY has actually been shown to correlate with insulin resistance. So there is some significance with this pathway with regards to diabetes and insulin resistance. So what we did was we looked at first acetyl-CoA levels or concentrations in the childhood onset and adult onset groups. These are females with either childhood onset or adult onset obesity. And as you can see, this is the open, I guess, boxes are those with the childhood onset obesity, and the stripe are adult. And as you can see, there are differences between those with childhood onset and adult onset obesity, where they had lower, those with childhood onset obesity actually had lower acetyl-CoA concentrations. And you can also see actually that this is specifically very much so in the femoral region as well. And then comparing the open and striped bars again, we see lower cytosolic acetyl-CoA levels in that the lower cytosolic acetyl-CoA levels correspond with lower ACLY levels as well. So in fact, our data show that, and our data, so we can see that that's reflective. And our data actually show that this correlates quite well with the cytosolic acetyl-CoA that we measure. And this may have implications to greater diabetes risk observed in those who are persistently obese from childhood, as lower ACLY has previously been shown to be associated with insulin resistance. So, since acetyl-CoA is closely linked to mitochondrial function, we also examine mitochondrial function of subcutaneous adipose tissue depots through measuring electron transport chain complexes. And here we can see that with regards to the electron transport chain complexes in the abdominal subcutaneous and the femoral subcutaneous adipose tissue depot, we see lower complexes in the childhood onset groups in complex 2 and complex 4. And interestingly, complex 4 has been associated or recognized as a sign of adipose tissue dysfunction that's associated with aging. And then the ratio of these complexes to complex 5, which is your ATP synthase, is also significantly different in both the childhood and the adult onset, between the childhood and the adult onset groups. Whereas you can see those with the childhood onset obesity have lower complex ratios. So this suggests impaired mitochondrial function in the subcutaneous adipose tissue of those with childhood onset obesity, especially in the femoral adipose tissue region. So impaired mitochondrial function in those with childhood onset obesity may be linked to a greater risk of various metabolic diseases, including diabetes in these individuals. So at the tissue level, what I've shown you is that both age and age of obesity onset contribute to the accumulation of adipose tissue macrophages. I also showed you that adipose tissue fibrosis is affected by age and age of obesity onset, and childhood onset obesity has less acetyl-CoA, ACLY expression, along with impaired mitochondrial function in subcutaneous adipose tissue, especially in the femoral subcutaneous adipose tissue region. At the cellular level, adipose tissue can expand by two main processes. One is through fat cell hypertrophy, where there's an increase in fat cell size, and the other is through fat cell size, which is fat cell number, which is adipose tissue is more hyperplastic. So in other words, we're increasing fat cell number, and then increasing fat cell number is increased in hyperplasia. So this is significant because it is thought that with the increase in the amount of hypertrophic adipocytes, in other words, as our average adipocyte cell size increases, there are various metabolic derangements that accompany that. And that includes these cells appear a little bit more likely to die. And also that those adipocytes that die can result in the increase in the recruitment of immune cells in the tissue. So they tend to be more promote greater inflammation as well as an increase in immune cells. So with regards to age of obesity onset, earlier studies have shown actual tissue differences between those who've had childhood onset obesity and those who've had adult onset obesity. Those who had childhood onset obesity were considered to be more hyperplastic and to have more hyperplastic adipose tissue, and those with adult onset obesity were considered to have more hypertrophic adipose tissue, or adipocytes, I should say. But these studies, because they were conducted in the 1970s, they were very cutting edge and revolutionary at the time, but things have shifted, right? So in these studies, subcutaneous adipose tissue was assumed to be uniform. So they might be taking, like, for example, subcutaneous adipose tissue from one area and compare it to another and just say that, okay, well, then we can see that there's differences in hyperplasia or hypertrophy, or they might be combining the adipose tissue from two different areas, okay? Also, at the time studies were performed, we lacked the ability to be able to quantify regional subcutaneous adipose tissue accurately. So total fat mass was used to calculate the adipocyte number instead of like specific regional depots, as we can do now with DEXA. So we sought to overcome these limitations in our studies to better understand differences in cellularity between childhood and adult onset obesity. To this end, we conducted a study that examined effects of obesity onset on adipocyte cellularity in males and in females. Here we have the open circles being females and then the closed circles that are males. So let's start at the top, taking a closer look at abdominal subcutaneous fat cell size and number, like here. So on the left, you can see that in the abdominal depot, in those with childhood onset obesity, there's a smaller cell size in females in childhood onset compared to adult onset obesity, but in males, there's no differences. And then moving to the right, for adipocyte number, we can see females with childhood onset obesity have much greater number of adipocytes compared to those females with childhood onset obesity, as well as males with either childhood or adult onset obesity. And then moving down, we're going to look at the femoral subcutaneous adipose tissue. And in contrast, we can see that in males, in the femoral depot, they had a greater adipocyte volume. So in other words, greater fat cell size compared to those with adult onset obesity. And then moving over a little bit more to the right, we see that males with adult onset obesity have greater adipocyte number compared to the other three groups. So what does this mean? Well, we took the fat cell size to number ratio and converted it to a Z-score. And what you can see here is that the higher the Z-score, the more hypertrophic the adipocytes are considered to be, and the lower the Z-score, the more hyperplastic the adipocytes were considered to be. And so, as you can see, that females with childhood onset obesity tend to have more hyperplastic adipocytes compared to those with adult onset obesity. And it doesn't seem to matter so much with regards to age of obesity onset in males. And in the femoral depot, males with adult onset obesity tend to have more hyperplastic cells in the femoral subcutaneous adipose tissue than either females or males with childhood onset obesity. So whether fat cells are hypertrophic or hyperplastic seems to depend not only on location, but also depend on sex and age of obesity onset. Now let's have a look at differences in fat cell size in visceral and subcutaneous adipose tissue in the study that I previously spoke about, where we compared age versus age of obesity onset. And what we see here is that in all groups, we see that visceral adipose tissue has smaller fat cell size compared to abdominal subcutaneous adipose tissue. Okay. And that's kind of expected because we've seen that in other studies. This just recapitulates that, but we see that there's no difference in terms of age or age of obesity onset. However, we can see that over here, those with the in the childhood young group, if you look at the this is not significant, but if you look at the subcutaneous adipose tissue here, it's a little bit, it kind of is like a little bit lower than the others, but visceral adipose tissue, you can really see that the fat cell size is significantly smaller than in the other groups. And this one is the group that would most accurately reflect the previous study, and it's kind of aligned with the findings that we had from our previous study. So therefore, the results suggest that perhaps both age and age of onset could affect adipocyte size differently in these depots. Oops. Another cellular aspect we examined was that of cellular senescence. So cellular senescence is a state of permanent cell cycle arrest. In other words, I kind of was explaining this to someone the other day, and it's almost like the cells being postmenopausal. Like they cannot proliferate, they cannot differentiate, they cannot, like, they're just there and they don't do anything. Okay, so the cellular senescence prevents, as I said, the proliferation of age and damaged cells. However, cells in this state also develop a senescence associated secretory phenotype, which is inflammatory. And cellular senescence can be initiated by different triggers, and these triggers can include, for example, short or DNA or damaged telomeres, or oxidative stress. And these triggers end up resulting in a DNA damage response, which the cells need to respond to. And one way they respond is to activate tumor suppressor protein P53. And if DNA repair is delayed or not possible, then the persistent P53 increases can increase cell cycle, cyclin, I should say, dependent kinase inhibitor, P21, which is also, both of these are indicators of cellular senescence. So given that cellular senescence is associated with aging, and that we theorize those with childhood onset obesity are at a greater physiological age, we examined whether there were differences in cellular senescence between those with childhood onset obesity and those with adult onset obesity. And we hypothesized that those with childhood onset obesity would have greater markers of DNA damage and cellular senescence than those with adult onset obesity. Here we have female participants. The average age of these participants was 31, and their BMIs were 33. So they were like kind of not so obese, like they were type 1 obesity. They had type 1 obesity, and they were relatively younger adults. So let's first look at pre-adipocyte DNA damage. Again, here, childhood onset obesity is depicted in purple, and the adult onset obesity is depicted in green. And as you can see here, there was an effect of group where those with childhood onset obesity actually had greater DNA damage than those with adult onset obesity, which is aligned with our hypothesis. As well, you can see that the abdominal region actually had greater DNA damage compared to the femoral region. Also, if we look at DNA repair, we see that in those with childhood onset obesity, the abdominal DNA markers of DNA repair were similar in the abdominal and the femoral region. And in adult onset obesity, the markers of DNA repair in the abdominal depot were smaller than in the femoral subcutaneous adipose tissue depot. Next, again, if you look at markers of cellular senescence, once again, we have a group effect where those with childhood onset obesity had greater markers of cellular senescence than in those with adult onset obesity. And this was also, once again, different by region, where overall those in the abdominal region had greater cellular senescence than in the femoral region. So at the cellular level, I've shown you that subcutaneous adipose tissue is not uniformly hyperplastic in childhood onset obesity and hypertrophic in adult onset obesity. In females, age and age of obesity onset affect fat cell size in abdominal, subcutaneous, and visceral adipose tissue differently. And preadipocytes in the abdominal and femoral subcutaneous adipose tissue of females with childhood onset obesity had greater DNA damage and markers of cellular senescence compared to those with adult onset obesity. So what are the implications of these outcomes on disease risk? Well, in our study where we examined cellularity, we found that in females with childhood onset obesity, that abdominal subcutaneous adipose tissue fat cell hypertrophy correlated better with various cardiometabolic risk markers that we measured. And in females with adult onset obesity and males regardless of their age of obesity onset, we found that femoral subcutaneous adipose tissue fat cell hyperplasia correlated better with cardiometabolic risk. Now we'll look at our age versus age of onset study in females. And you'll see over the next few slides that both age of obesity onset and age matters with regards to these relationships. At the top, you can see markers. There are tissue markers that we measured. On the left over here, you can see the various plasma risk markers that were measured. And you can see that there's no, in the adult young group, this is those that are younger, have the shortest obesity duration, no associations, right? In the child young group, we also see no associations. But as we get a little older and we have the adult individuals with adult onset who are older adults, we see that there is starting to see some associations, primarily between the triglycerides and those macrophage markers. But when you look at the individuals who in our child-old group, the childhood onset had, this is the individuals that had the greatest duration of obesity because they've had obesity since childhood and they were older. Okay, we see that adipose tissue characteristics were positively and well associated with our various metabolic markers and in several places. And so collectively, the adipose tissue might become increasingly more pathogenic with greater lifetime exposure to obesity. So we could hypothesize that perhaps these older adults with childhood onset obesity are also maybe perhaps a bit more sensitive to cellular changes happening in adipose tissue. So reflecting on our learning objectives, I hope that in attending my talk, you have you'll be able to identify at least 3 comorbidities of obesity that are associated with aging. I also described various characteristics in the adipose tissue which promote aging, and list at least 3 biological or cellular mechanisms shared by obesity and aging. So I'd like to thank you very much for your attention. And of course, I'd like to acknowledge those members of my lab and our funders who have made very important contributions to this work. And of course, much of the studies that I presented today were conducted by my postdoc, which is Bjorn Tam. These are my previous student, Jessica Murphy, and Laurent Turner. Okay, thank you very much.